Okay, think about your email inbox for a second. You've got spam, and you've got the important stuff. You need a system, right? A line in the sand to separate them. But here's the real question. How do you draw the smartest possible line? Well, today, we're diving into the machine learning algorithm that's obsessed with that very question. It's called the support vector machine, or SVM for short. Let's get into how it pulls it off.
So, here's what's on the docket. First, we'll talk about finding the widest road between our data points. Then, we'll figure out how to deal with the real world, when things get messy. After that, we'll pull back the curtain on SVM's secret weapon, the kernel trick. And to wrap it all up, we'll see where this thing actually gets put to work.
All right, let's jump right into part one, the widest road. The whole idea here, the very heart of SVM, is finding the absolute best, most confident dividing line you can possibly draw between two groups of data.
So, if you look at two clusters of data, you could probably draw a bunch of different lines that separate them, right? But are all those lines created equal? SVM says absolutely not. See, the best boundary isn't just a line that does the job. It's the one that gives itself the most possible breathing room. It wants to be as far away from the nearest data points on both sides as it can get. It's all about finding that maximum safety zone.
Now that fancy decision boundary we're talking about, it has a technical name, a hyperplane. And I know, that sounds kind of intimidating, but don't worry about it. In 2D, like on a screen, it's literally just a line. If you had 3D data, it would be a flat plane. And in higher dimensions that we can't even visualize, well, it's still the same concept. The whole game is to find the hyperplane that has the widest possible margin, that big, empty street separating the two neighborhoods of data.
Okay, so who decides where this perfect line goes? What actually determines its position? Well, that's where these key players come in, the support vectors. These are the data points that are living right on the edge. They're the ones closest to the hyperplane, sitting right on the curb of that wide street we drew. And they are everything. They are the most important points because they, and they alone, define where that hyperplane is. You could move any of the other points around and nothing would change. But if you nudge one of the support vectors, the entire boundary has to shift. They literally support the whole structure, hence the name.
This whole idea of a perfect, wide margin, it's really elegant. It's called a maximal margin classifier. And when your data's perfectly clean, it's awesome. But let's be real, when is data ever perfectly clean? The real world is messy. You've got outliers, you've got points that kind of stray into the wrong territory. So what do you do when a perfect, straight line just isn't possible? What happens when you can't separate everything without making at least one mistake?
And that question leads us right into our next section, dealing with the messy world. This is where we learn how to give our model a little bit of flexibility by talking about something called hard versus soft margins.
This is a really important trade-off to understand. Think of a hard margin as a total perfectionist. It has one rule: 0 misclassifications. It must separate every single data point perfectly. The big problem? Just one single weirdo outlier can totally throw it off and lead to a terrible boundary. On the other hand, you've got the soft margin. It's more realistic. Its goal is still to find a nice wide margin, but it's okay with a few points being on the wrong side, or even inside that margin. It's this flexibility that makes it so much more robust and way more useful in the real world.
So how do we control just how flexible our model is? We get a tuning knob, and it's called the C parameter. The easiest way to think about C is as your budget for mistakes. If you crank C way up, setting a really large value, you're basically telling the model, I hate mistakes, your budget is tiny. This forces the SVM to create a really narrow margin to try and get every point right. But if you use a small C value, you're being more generous. You're saying, hey, your mistake budget is bigger. I care more about a wide, stable margin, even if it means a few points end up on the wrong side.
And this choice, this C parameter, plugs us directly into one of the most famous concepts in machine learning, the bias-variance trade-off. Let me break it down. A large C, with its narrow margin, is trying really hard to fit your training data perfectly. That's low bias. But it might be too specific, making it fragile and likely to perform poorly on new, unseen data. That's high variance. We call that overfitting. On the flip side, a small c creates a wide, general-purpose margin. It might not be perfect on the training data, that's high bias, but it's more likely to do a good job on new data, that's low variance. So finding that Goldilocks C value is totally key to building a model that actually works.
Okay, great. So soft margins let us handle some outliers and a little bit of messiness, but what if the problem is more fundamental?
What if your data is arranged in, say, a circle inside another circle? No straight line in the world, no matter how soft or hard the margin, is ever going to separate that. So what now?
This, my friends, is where SVM goes from a clever algorithm to something that feels like pure magic. Welcome to our third section, the kernel trick, and it's all about thinking in a higher dimension.
The logic behind this is, well, it's brilliant. If your data is a tangled mess in its current dimension, like a 2D plane, the kernel trick's whole job is to project it into a higher dimension where it isn't a mess. Here's the best analogy. Imagine you have red dots and blue dots mixed up on a flat piece of paper, and you can't draw a line to separate them. The kernel trick is like grabbing the red dots and pulling them up off the paper, into the third dimension. All of a sudden, they're floating above the blue dots. Now, separating them is easy, right? You just slide a new sheet of paper, or hyperplane, right in between. The impossible problem just became ridiculously simple.
Okay, but here's why they call it a trick. Actually doing all that math to transform every single data point into a higher dimension, that would be a computational nightmare. Super slow, super expensive. Kernels are these awesome mathematical shortcuts that let the algorithm get all the benefits of working in that higher dimensional space without ever actually having to go there. It's like finding a secret tunnel. You get the result of the separation as if you were in 3D, but you do all the math in your original 2D space. It is so clever and efficient.
And of course, we've got a whole toolbox of different kernels for different jobs. The linear kernel is just your basic SVM for when a straight line mostly works anyway. The polynomial kernel is great for creating smoother, curved boundaries. And then there's the big one, the radial basis function, or RBF kernel. This one's the superstar. It's incredibly flexible and can create all sorts of complex, even circular boundaries. Honestly, it's so powerful that it's usually the default choice, the first thing you try when you have a tricky problem.
Okay, so we've built up this really powerful, really flexible algorithm. Let's land the plane in our final section, SVM in action. We're going to talk about the good, the bad, and where you'll actually see this stuff in the wild.
So let's get real about the pros and cons. The advantages? SVM is a beast in high-dimensional spaces. We're talking about data with tons and tons of features, like image recognition or genetic analysis. It's also super memory efficient, because it only really cares about those support vectors. Now, the downsides. It can get pretty slow if you throw a massive data set at it, and its performance is super sensitive to getting those tuning parameters, like C and the kernel choice, just right. It's not always a plug-and-play kind of model.
And get this, SVM isn't just for putting things into boxes for classification. You can actually flip the whole idea on its head and use it for regression. That's when you're trying to predict a number, like a price or a temperature. It's called support vector regression, or SVR. And instead of trying to draw a street that keeps everyone out, SVR tries to draw a street and fit as many data points as possible inside of it. Pretty cool, right?
This versatility is why SVM is such a powerhouse. You see it everywhere. It's used in facial expression recognition. It's one of the classic foundations of spam filters. It's amazing for analyzing text to figure out sentiment, and it's even used in super complex fields like bioinformatics to classify genes. It really is a workhorse algorithm in the world of machine learning.
So let's just quickly recap what we've seen. We started with a really simple and clean idea: find the widest possible road to separate two groups. Then, we made it tough enough for the real world by giving it a mistake budget with soft margins. And finally, we gave it actual superpowers with the kernel trick, letting it solve problems that looked completely impossible at first glance. It's quite a journey.
Look, SVM is an absolutely incredible tool. It's a master at finding the best possible boundary once we've told it what to do. But that leaves us with a much bigger, more human question, doesn't it? We have this amazing algorithm that can draw the perfect line, but it's still up to us to decide which things in the world are worth separating in the first place. And that, well, that's a question no algorithm is ever going to answer for us.